Hello everyone, my name is Pirazh Khorramshahi and I will be presenting our work titled Lightweight Delivery Detection on Doorbell Cameras. This work was done as my internship project at Comcast Applied AI Research in collaboration with Wu, Tianchen Wang, DeLuccia, and Hongcheng Wang. First, I would like to start with the definition and the necessity of delivery detection, as this is a novel task that was never considered before. The official definition of delivery detection is to detect the delivery of merchandises, including packages, food, groceries, at the front doors, to provide timely notifications. The reason that this task is interesting lies in the fact that it can be a crucial feature in smart homes that can prevent porch piracy as well as food perishing. I have to emphasize that delivery detection is different from package detection that is currently commercialized. In case a package is invisible due to occlusion, for example, it does not imply that a delivery event did not occur. Additionally, existing solutions for package detection are all cloud-based, which raises privacy concerns, require higher bandwidth, has higher latency, and typically contributes to increased subscription fees. There are a number of challenges associated with delivery detection. Among those are: first, high variations in type, shape, and size of deliveries. Second, delivery personnel of different courier services have diverse outfits. Third, there is a high temporal variation in the duration of deliveries. And lastly, limited resources of doorbell camera systems is used to avoid cloud processing. Now, with that being said, the outline of this presentation is the following. As there is no prior art, first we establish a baseline system to detect deliveries. By discussing its shortcomings, we transition to our proposed lightweight delivery detection system. Next, the curated dataset for detecting deliveries is discussed so that we can evaluate both the baseline and proposed systems. And finally, the evaluation results are presented. To detect delivery events in our baseline design, we assume that we have a short clip containing multiple frames. A person detector scans all the frames to detect people. Image crops of detected people are passed to an image classifier to classify people as delivery versus non-delivery personnel and yield a delivery score. MobileNet SSD and EfficientNet B0 are considered for this purpose. Delivery scores are max pooled to decide whether a delivery event has occurred. This model, despite being simple, intuitive, and easy to implement, has a number of shortcomings. First, it's not an end-to-end pipeline. Second, it suffers from a high false positive rate due to max pooling over multiple frames. And third, information gathered in a temporal axis is not considered here. Based on these shortcomings, we propose our novel lightweight delivery detection system, which is triggered upon detecting motion in a camera feed. The detected motion serves as a proposal to be classified. Once we have a motion proposal, it is uniformly sampled along temporal axes and then processed by a 3D network to account for spatio-temporal cues. The benefit of this proposed method is that it is simple, intuitive, and end-to-end approach, and capable of accounting for temporal information. The issue that is associated with this model, though, is that the complexity of the 3D model can be overwhelming for the resource-limited platform, such as the doorbell camera. Our system has a motion detection mechanism to detect foreground-background segments based on the mixture of Gaussians. After motion detection, those are tracked to check whether they are active for a certain time and if they have moved. This allows to filter out many trivial motion events. Afterwards, using tracked motion events, we crop the corresponding cuboid for further processing. As mentioned earlier, we need to ensure that a mobile-friendly architecture is used for the 3D model. Transformer models are not suitable as their utility in mobile applications is limited to 2D. On the other hand, 3D versions of popular mobile CNN networks, including MobileNet version 1, MobileNet version 2, ShuffleNet version 1, ShuffleNet version 2, and SqueezeNet can be considered. In our preliminary experiments, we noticed that MobileNet version 2 shows a higher performance ceiling, and therefore we use it in our experiments. To enhance the robustness of extracted spatio-temporal features, we designed a novel semi-supervised attention mechanism via excitation layer to maintain the original computational complexity during the runtime. This is inspired by the notion of curriculum learning, to simplify learning in earlier stages of training and then making the task more realistic as training progresses. Since people are main players in identifying delivery events, this layer excites parts of the intermediate feature maps that corresponds to the location of people. The degree of excitation reduces as training progresses. The impact of such excitation is visible in this figure. Another technique we use in our system is to change the objective function so that the network is tasked to collect evidence for each of the delivery and non-delivery classes by assuming a Dirichlet distribution over class probabilities. Additionally, we regularize this training such that the network is encouraged to produce zero evidence for all classes in case it makes wrong predictions. Also, it is calibrated to favor correct and confident results or wrong and uncertain ones. To evaluate our models, we gathered 5,477 videos from 339 residences that contributed to the total of 3,625 delivery and 7,248 non-delivery events. To measure the accuracy, the F1 score, mean average precision, false positive rate, and classification accuracy are used. First, we run a package detection system on this dataset to declare delivery detection whenever it finds a package. Noticeably, it suffers from a high false positive rate. The baseline system is a substantial improvement over the package detection. However, due to the absence of temporal information, it falls short of our proposed system. Additionally, we see that both our semi-supervised attention and evidence-based delivery detection contribute to the performance improvement without incurring any additional computational cost. In terms of efficiency metrics, we can see that the inference time of our approach is about 1.5 times the baseline. However, we have to emphasize that the baseline model needs to process multiple frames to get to a final score. Also, the binary size and the number of operations that is performed by our model is much smaller compared to the baseline. Finally, since our model can quantify uncertainty as a value, we can choose a minimum certainty level when considering predictions. Learning that threshold from our validation set, we can further improve the performance. Here, you can also see some uncertain predictions from our network. They all show some flavors of delivery events, despite not